Okay, so we're on to the next module here, and we're going to lump oxidation state 2 and 3 functional groups into one. Some of this stuff we're going to just briefly cover because from the prior module with oxidation, we've already talked about some of these functional groups. So we'll spend more time with the new ones, specifically acetals, imines, enamines, aminals, and then we'll look at carboxylic acid functional group transformations. So again, this is all layered around this oxidation state of the carbon concept. And so really, some of this is just functional group transformations where the oxidation state stays the same. So that's why these have different names like acetals and imines, that sort of thing. So as we learn these transformations, that sets us up for the next module 5, where we focus on one specific carbon, the alpha carbon. We'll slowly introduce that in this module. And then the semester is going to end with the chemistry of biomolecules, so carbohydrates, which are basically a carbon chain with an aldehyde at the end and just a bunch of alcohols. But because of all of that stuff, it's a special type of molecule. We'll look at amino acids, so those form peptides and proteins, and then how do those biopolymers form the molecules of life, and then that's your kind of send off into the biochem sequence if you take that, or cellular and molecular biology. So I think the last part of this semester, it's really setting you up to be successful in those other classes, because once you start looking at larger structures, it can get a little bit more challenging to understand what they are doing. But fundamentally, they're still organic molecules. And if you break them down into those functional groups and what the reactions are, it's a little easier to digest. So we'll start with aldehydes and ketones. Again, looking at sort of nomenclature, physical properties, spectral signatures, some new reactions, and then the review of some old ones. So aldehydes and ketones, we'll start with aldehydes here. And the line abbreviation is that CHO. So if we expand that CHO becomes that bonding pattern. So the carbonyl is at the terminus of the carbon chain. That's what defines it as an aldehyde, because you have that sp2 hybridized carbon H bond. In terms of the nomenclature, if we look at the carbon count, you basically take the name of the alkane, you fire the E and hire the AL, and then that indicates that it's an aldehyde. So this carbon is, again, sp2 hybridized, and it's oxidation state 2. So looking at the carbon count, for one carbon, methane becomes methanal, and it would be written like that in the line form. And then we can see the different physical properties. So all of these are up until the 5 count. These are the just linear straight chain aldehydes. The last one here says benzaldehyde. That's where you have the aromatic ring. Bonded to the aldehyde. And that is, does anyone know what that smells like? It smells like almonds. So Apparently hydrogen cyanide also smells like almonds, so that's a chemical indicator if you're working with such things. But I think benzaldehyde is it's in one of the flavorings. So like if you get like almond flavoring for your cake or something, it has a synthetic benzaldehyde in it. So the main thing is, the carbonyl has to be at the end of the chain. That's the aldehyde, and then you're looking for the Al to know that it has that structure. So the aldehyde CHO group cannot be in a ring, but the other stuff bonded to it can have a ring. So the nomenclature changes a little bit, and what you'll see is that these all end in this very long word, carbaldehyde. So if we slice it right there, the carbaldehyde is this part, and then the front part of that name is just that ring size. So as I said, that carbon is at oxidation state 2. And as a review of nomenclature, you'll see one or two nomenclature problems on your final. The rules are basically that the highest oxidation state functional group becomes the parent. So that's the suffix at the end of the name. In the cases shown below, we have these polyfunctional molecules. And if we identify them, we say, okay, that's a carboxylic acid. That carbon's oxidation state 3. This is an aldehyde. It's oxidation state 2. So the 3 wins, so that it's named as a parent of an acid. And so there's 1, 2, 3, 4, 5 carbons. So that's the pentanoic acid. And the aldehyde is no longer the parent, so it's named as a substituent. And so when it's that as a substituent, it's called a 4-mel group. So one carbon has that sort of common thing form. So like formic acid is, the little thing in ant bites. So at the 3 position is the 4-mel group. And then you can see that with these other cases when you, that should be 2, 3, 3, and 2. You apply that analysis to it to figure out the parent, and then whatever else is a substituent. So this question says, what is the highest oxidation state in the functional group in 4-bromo, 2-4-mel, 3-hydroxy, and then butanoic acid? So if we convert that name to a structure, we have a 4-carbon acid. So that's the numbering of the chain. Then we can go back in and put the substituents. So at position 4 is bromine. 2 is the 4-mel group. And then 3 is the alcohol. So what I'll do in blue is just write the oxidation states. So 3, 2, 1, and 1. So the acid has the highest oxidation state, so it's the parent. And as we learn more reactions, more functional group transformations, this oxidation state analysis is again helpful to understand how you rank the different reactions in terms of sequencing them. So how do we know that we have the aldehyde present in a molecule? IR is a really strong indicator because there's two diagnostic signatures. We have the carbonyl in that normal 18 to 1700 region, but then this is what differentiates it from a ketone or the other carbonyl containing functional groups, is that specific sp2 hybridized H stretch that occurs to the right, or lower wave numbers than all the other CH stretching. Another strong indicator is the proton NMR, where that aldehyde CH is normally in the 9 to 10 range. So I think it was my other class for Organic 1. We just finished spectroscopy last week. Normally that hydrogen will appear as a singlet, but sometimes if there's hydrogens over here, it can couple, and so it might be like a doublet or a triplet or whatever. But as long as you see something that looks, like a signal that integrates to one, that's usually a strong indicator of an aldehyde. And then carbon NMR, obviously you must have the carbonyl carbon between 180 and 200 or 220. So for the 4-carbon aldehyde butanal, the CH stretch is this thing right over here. So that little piece coming off, again, further to the right, coupled to that strong carbonyl stretch. So again, usually that is pretty strong, and it has that separation up here from everything else. So when you see that carbonyl, the next thing I would suggest is look over here to see if that thing is hanging off there. So the carbonyl group, again, has that polarity where the oxygen's delta minus, the carbon's delta plus, and we saw that when we were learning about reductions, either with the hydride reagents or the Grignards. And we can rationalize the reactivity if we look at a resonance form. Where we put those pi bond electrons onto oxygen, and so that carbon becomes plus. That means nucleophiles will attack it. And so ultimately it will be reduced from a carbonyl to an alcohol. So we have that polar covalent bond. The carbonyl group can only act as a hydrogen bond acceptor due to the oxygen lone pair. So to a certain carbon count, certain form of structure, these things can be miscible or slightly miscible in water due to that hydrogen bonding interaction. So that would be the acceptor and that would be the donor due to that OH bond. If we were comparing say the same carbon count, so 3-carbon alcohol versus 3-carbon aldehyde, alcohols will always have a higher boiling point than aldehydes because these are donor and acceptors. So the other OS2 with carbonyl is the ketone. Now we're taking that carbonyl and moving it to the internal carbons of the chain. So that carbonyl is now bonded to 2 carbons on either side. And from that arises 2 scenarios where you can have a symmetric ketone or non-symmetric, where your carbonyl is where you're starting, and then you're looking at what's bonded to each side. So if they're the same, it's symmetric. If those groups are different, it's non-symmetric. And one thing we'll notice when we start looking at the carbon count, we now have to specify what carbon is bearing the carbonyl group, because it can be anywhere along the carbon chain. The aldehyde, it has to be at the end, so we don't specify a number with that. So for 3 carbons, we get 2-propanone, so that's this molecule. Just by saying propanone, it has to be at the 2 position. But as we increase in carbon count, we'll see that we do have to start specifying it. So this molecule here is called butanone. When we get up to 5-carbon count, we can see that the carbonyl can be either at the 2 or the 3 position. So don't want to do that. So that would be the 2-pentanone, or we could have the isomer, the 3-pentanone. So we have non-symmetric and symmetric. And the last 2, these are what I'm going to say aromatic ketones, where one of those groups is a benzene ring. These can be named different ways. One way is you say like methyl phenylketone, where you're just naming the side chain groups and then throwing ketone up on the end. So this would be ethyl phenylketone. But most often they have these common names, which really give you no indication of kind of what the side chains are. So this one is acetophenone, and then this other one is propiophenone. So say on your module exams, if you're given that sort of nomenclature, and if you don't know it, you can go to your textbook or just Google the answer. So as opposed to aldehydes, you can have cyclic ketones now, because as you go off from the carbonyl, you have carbon substituents on either side. And really, for a cyclic ketone, you're just tethering those terminal carbons into a ring. So cyclopropanone, the cyclo tells you it's a ring, the propane tells you it's 3 carbons, and the ONE is telling you that it's a ketone. So these molecules, you have a pi bond, you have a ring, and so overall, they'll have 2 degrees of unsaturation. It's a little boo-boo in here. This should say ketone. So ketones and esters are probably the 2 of the hardest functional groups to figure out with spectroscopic methods. So they'll both have that carbonyl stretch in the normal region. They'll both have a carbon in the C13 NMR between 180 and 220. And so if you're given a molecular formula and it has 1 oxygen, 1 degree of unsaturation, you could say it's probably a ketone. If it has 1 degree of unsaturation but 2 oxygens, it could be an ester. So that's when you get into the more ambiguous interpretation of the data is figuring out, these different carbonyl containing functional groups. So here we have butanone. And so there's the carbonyl. And you'll notice over here, we don't see any of that aldehyde H, so we know we can eliminate it. It's not an aldehyde. But as I said, if you were just given this IR and you didn't know the structure, there could be some ambiguity about whether there's an ester oxygen present as well. So sort of the same deal with ketones as aldehydes. The resonance hybrids show the reactivity that the carbonyl carbon is electron deficient, so it can be attacked by nucleophiles. And then we've seen those strong nucleophiles already, hydride H- or carbanions. What's going to be different for this module is that the strength of the nucleophiles will now be weak. They still add the same way, but once you form them, they can do things that are different from when that carbon is just reduced. So these are only H-bond acceptors for the same reason that we gave for aldehydes. So to a certain extent, they will be miscible with water, but as you start increasing the carbon count, that makes the molecule more lipophilic. So lipo meaning fat, philic meaning lover. So it's you can think of those things in different ways. Lipophilic is like carbon loving, or hydrophobic is like water hating. So depending on the context, you'll see those terms used. So those were the the nomenclature, the physical properties, the spectroscopic signatures. These next couple slides are the review from the prior module. Where in the oxidation reactions, if you take a primary alcohol, so again, it's the carbon bearing the OH group, has 2 hydrogens bonded to it. So for example, 1-butanol. So that's oxidation state 1. It's also a primary alcohol. We learned 3 different conditions, Des-Martin pyridinane, SWERN, and PCC. Any of those conditions will take that carbon to oxidation state 2. The hybridization then changes to sp2. And they're forming aldehyde. So just be familiar with, that how those reagents affect overall that transformation. So a reaction we saw in organic 1. Say we have an alkene where at least one of the carbons has a CH. We can treat that with ozone gas in the presence of a reducing agent, say triphenylphosphine. And essentially what that's doing is cleaving that double bond. So we're going to cleave that, and wherever there is an sp2 hybridized carbon, we're just making a carbonyl. So each carbon gets its own carbonyl group. And as long as you have an H bonded to that, you'll end up with an aldehyde. So if everything was carbon, 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 and carbon, then that would make ketones. Any questions? So the same set of conditions, but now we're starting with a secondary alcohol. So it's still oxidation state 1, but because it's secondary, any of those 3 conditions will produce a ketone. The alkene down here, every substituent bonded to the alkene carbons is carbon. So when we cleave that, each carbon becomes a carbonyl, and so therefore the things bonded to it are still carbon, and that makes them ketones. So that was kind of the last part of organic 1, where we talked about electrophilic addition to alkenes. In this case, we're actually cleaving that double bond, so it's called ozonolysis, which is cleavage by ozone. So let me just kind of show a sequence here. So say we start with 1-butanol, and then we do an oxidation. So now we're at oxidation state 2, and we've made butanal. We saw that we can add a carbon nucleophile to that. So say we're going to use CH3MgBr, so methyl magnesium bromide. That's a Grignard reagent. And then we work that up under acidic conditions. So that methyl group is added to that carbonyl. So overall, we started with a primary alcohol. We went up in oxidation state. The carbon nucleophile then reduces it back to oxidation state 1. But now we end up with a secondary alcohol. This reaction here, from aldehyde with Grignard to there, that's irreversible, meaning it can't go back the other way, because a negatively charged carbon is a pretty strong nucleophile. But what about when we have other nucleophiles that aren't strong? They're weak nucleophiles. How do they add to carbonyl groups? And what is the difference between strong and weak? The type of nucleophiles that we're going to look at are shown in this table here. So this is the functional group of the nucleophile. The electrophile it's adding to at oxidation state 2 is either going to be an aldehyde or a ketone. So alcohol reacting with an aldehyde gives an acetal as a product. So the names change a little bit based on what you're starting with. So acetal, ketal. We can use amines. Notice these are only primary or secondary. These form imines, so aldimine or ketamine. Secondary amine with either aldehyde or ketone forms an enamine. A nitrile forms a cyanohydrin. So alcohol was OH, thiol is SH. These form thioacetals or thioketals. And then water by itself forms a hydrate. Now the difference between the majority of these, I guess I'll put an asterisk by this one. We're going to start at oxidation state 2. with a carbon in a carbonyl that's sp2 hybridized. When we run this reaction, the product is still going to be oxidation state 2, but now the carbon is going to be sp3 hybridized. So there'll be a little nuance to these things based on what nucleophile we're using and how we move across the periodic table. So we'll show some reactions, we'll write some mechanisms, and a lot of this stuff is based on proton transfers. So let's just start with water. So we have this aldehyde plus water, and then we're making a hydrate. That carbon starts off at sp2 hybridized. The water does a nucleophilic addition. The hybridization changes to sp3. So we can identify that through 1, 2, 3, 4 sigma bonds. But look, now the oxidation state is still the same. Because now we have 1, 2 sigma bonds to 2 different oxygens. So that's equivalent to the carbonyl because you have a sigma and a pi, that's still 2. So what is the mechanism for why this happens, or how does it happen? So this aldehyde 2,2,2-trichloroacetaldehyde forms this thing, which is called chloral hydrate. And then, does anyone know who this guy is? Yeah, we need to bring back this sort of style, the suit and stash. So the reason this is well known is this guy's name was Mickey Finn. Have you ever heard of like knockout drops? So this guy owned a hotel in Chicago. And so the hotel had a bar, and wealthy patrons would visit the bar, and he would put that in their drinks, and it would knock them out, and then he would rob them for their watches and coins and whatnot. So it's called a Mickey Finn, give them a Mickey sort of thing, and then you can take their wallet or now their iPhone, whatever your pleasure is. So we want to understand what's happening to this oxygen. How do these other oxygens get on there? Another way of saying that so if I highlighted that oxygen in blue, is it retained as one of those in the product? Or does it leave by some mechanism? So based on the name of hydrate, the difference in molecular formulas between this and that, overall we've added H, H, and O, so that's water. So we've hydrated that carbonyl. I'm just showing the aldehyde part. The R thing can be whatever because it's not involved in the mechanism. So under acidic conditions, we have hydronium ion plus water. So we have an acid, water is our solvent. So this has to be a base. And a lone pair of the oxygen is going to act as a base to react with hydronium and do a proton transfer. So that gets protonated. We generate water, that's the solvent we're running the reaction in, so that's fine. That plus charge now goes on to that oxygen. And as I showed at the beginning of lecture, we can show a resonance form for the carbonyl. Where the plus charge moves from O to C. And what that is telling us is that carbon wants to now be attacked by a nucleophile. And the nucleophile is the water. So the arrow starts at the lone pair, points to the electron deficient center. Now that the plus charge moves down to that oxygen. So we're almost there. We take another molecule of water to do a proton transfer, and then that will regenerate our acid catalyst. So you'll notice that I drew these back and forth arrows here throughout. The reason for that is these reactions will set up an equilibrium, meaning that because you have a weak nucleophile, it's not fully going to convert to this unless you disturb the equilibrium. So Le Chatelier's principle. You either add, more acid to consume all this, or you remove the product as it's formed. So you need to disturb it somehow. But mechanistically, if you started with the hydrate, you could run this reaction in reverse to make the aldehyde. And so you'd push the arrows the opposite way. So I'll start that by drawing it in blue. So if we were starting with the hydrate, the first thing we'd have to do is protonate one of the oxygens. And so that would get us back here. And then from there, you're just running the arrows in reverse. Then you could isolate the aldehyde. The reason that's important synthetically, we know that the aldehyde carbon can be reduced, so nucleophiles will attack it. So in that, strong nucleophiles attack it in an irreversible sense. So because we can transform it into this, which is still oxidation state 2, you cannot reduce that carbon. So hydrides or Grignards will not attack that carbon. So if we have a sequence where we need to conserve that, we can protect the carbonyl as a hydrate. If we generalize this, so we started with water. You can really use any alcohol. And so what you would end up with, instead of OH and OH, these would be R groups from whatever alcohol you started with. So that's where you get these other names like acetal or ketal, again, depending on if you start with an aldehyde or a ketone, and then some other alcohol. So the example of that is with methanol. So notice what you see now on that carbon. You've added 2 equivalents of methanol to it. And you've retained that oxidation state. So in a synthetic sense, they're used as protecting groups, as we'll see in Module 5. The acetal carbon is what is crucial for carbohydrates to form ring structures, so 5 or 6 membered rings. And then we'll see those things present in DNA. So let me see what. One thing I do want to point out, if you're given a structure like this on an exam, you identify the carbon as sp3 hybridized at oxidation state 2. How do you know what it came from? Did it come from an aldehyde or a ketone? So once you have that carbon, look at both of these substituents. So I see a carbon, I see an H, therefore I know this has to come from an aldehyde. If it's carbon and carbon, it has to come from a ketone. So aldehydes, they form acetals, ketones form ketals. I always think of like, isn't there like a vodka name? Maybe it's ketel. Anyway, we have, let's do kind of a different demonstration of that. We'll start with cyclohexanone. And as a prelude to the next slide or two here, I'm going to start with this alcohol, but it's a 1,2 alcohol or a diol. We know that that carbon has to form 2 sigma bonds to 2 different oxygens. this molecule has two alcohols. So the alcohols are tethered together by that carbon chain. So I'll write the mechanism, but what I want to do now is kind of show you a way of thinking about how you can figure out what the product is going to be without having to go through all these steps. None of these carbons are going to change, so it's still going to be a six-membered ring. That blue carbon has to go from a carbonyl now to a ketal. So it has to have two sigma bonds to two different oxygens. If we look at what we're starting with, they're in the same molecule, so they have to be tethered together. So up here, I need to draw a ring. What size ring should that be? So that carbon is staying there, so that's one carbon. When we look at our alcohols, we have 1, 2, 3, 4 atoms. So 4 plus 1, this is going to be a 5-membered ring. So we'll go through the mechanism, but anytime you're given something like this, you should be able to identify, is it coming from an aldehyde or a ketone? And then what were the alcohols used? So in this case, again, they're tethered together, so that's how we end up with a ring. Any kinesiology majors in the crowd? So PT in this sense is proton transfer, not physical therapy. So we're activating the carbonyl. That's going to make it more susceptible to attack. And we're using that diol as a solvent as well, so it's present in a large excess. So it's going to attack that carbon. So now we need to get this other oxygen bonded to that same carbon, meaning we have to get rid of this OH. But we're under acidic conditions. So that can't leave because it would leave as hydroxide. So I'm going to do two things at once here. So two different proton transfers. So we generated water before, from the hydronium. So I'm going to have water deprotonate that oxygen. And then I need to protonate the other one. So I'll use the hydronium there. So one loses an H, the other one gains an H. And so that's any Chicago Bears fans in the crowd. It's the proton shuffle. Probably none of you were born in like 1984 when the Chicago Bears won the Super Bowl shuffle. Okay, so you're just shuffling things around because we're in acidic medium and we have to account for the charges of the intermediates. So what happens next is an elimination. That oxygen lone pair is going to push out water. So I might just erase this for now. So same thing, we can show the plus charge going to the carbon. Now that second alcohol is tethered on there, so it will come around and attack that. And so that's 5 total atoms in the ring. And then that's the last step to get to our ketal. So synthetically, again, we use it because we've protected that carbon. Are there any marine biology majors in the crowd? No? Okay. So again, that functional group is a ketal. Based on how it's connected to that carbon, this is called a spiroketal. That means you have these 2 rings and they sort of sit orthogonal to one another. So there are these sponges that exist in oceans and lakes and stuff that produce natural products that form these spiroketals. And some more of the complex ones end up having like really potent biological activity. So like anti-cancer type activity. And when we get into the next module, and we start learning about how like nature makes carbon-carbon bonds. It does it in such an arrangement that you get a natural pattern of oxidation states. So every so often you get certain oxidation states, and then conformationally these things can react within the molecule to form these certain types of ketals and things like that. And so that gets into like genetics and stuff, like how does a plant make these things in kind of repeating patterns. But if you can identify the functional groups, the oxidation states, that'll lead you into a smoother understanding of how nature makes these things, and ultimately how they're biosynthesized in your own body. Okay. So the next example I want to bring up, we talked for maybe 30 seconds about thiols. And so there's not a whole lot of sulfur chemistry for this sequence of 255 and 256, but there are some things that we want to know because sulfur behaves differently than oxygen. In this example, we're still forming I guess in this case an acetal, because we're starting with an aldehyde. So we've replaced those two oxygens with sulfur. And so now we have that oxidation state 2, but now since these are sulfur, that allows us to do something the oxygen variant can't do. So mechanistically, you would sort of push arrows the same way to form that functional group. And what makes this different now, this thioacetal, that oxidation state 2 can be completely reduced to 0 with hydrogen gas and then this form of nickel. And synthetically, that's kind of useful because anywhere you look in a molecule where you see an oxidation state 0, you can kind of think backwards that if this was a thioacetal, I could reduce it to this. The thioacetal is then made from the carbonyl. So that allows us to get some flexibility in dealing with, oxidation state through a complex sequence. So that's, one way of doing that, like a historical method. Nowadays, it's probably not as employed that common. As you can imagine, that dithiol smells, and then reducing it is not the easiest thing in the world to do. But it's a strategy to hop through those oxidations. So let me say, let's see what all that's useful for. So we're going to look at some molecules that are at different oxidation states, and we're going to have to, put one of these protections, deep protections in so that we get the right product out. Remember when we were learning about reductions, there was lithium aluminum hydride and sodium borohydride. So lithium aluminum hydride was kind of the hammer. It affected all of the oxidation states. Sodium borohydride was just aldehydes and ketones. And so now that we know how to protect carbonyls, we can put that into sequences to conserve things as we move along. I think we have some problems. So let's consider this transformation shown here. The first thing I want to do is just identify the oxidation state. So we have an ester, that's 3. And then we have a ketone, that's 2. In the product, we have the ketone, that's still 2, and now we have a primary alcohol, that's oxidation state 1. So the issue is we want to reduce the ester, the oxidation state 3. So we have to use lithium aluminum hydride because that's the only thing that will reduce it. But lithium aluminum hydride reduces oxidation states 2 and 3. So because the ketone is conserved, that means we have to make it inert first. We got to take it out of play. Then we can do our reduction, and then we can unmask it. So in terms of choosing these reagents, maybe what I'll do is just pick the steps, then I'll draw what the products of those steps are. So the first thing we want to do is protect the ketone. And so we would say E would be the best choice to do the first step. So the other thing I want to mention, the benefit of this stuff is kind of the opposite of the lithium aluminum hydride. The protection is only acting on aldehydes or ketones. These things don't act on the oxidation state 3. So now we've taken the ketone out of play. The acetal will not react with LAH. So now the second step, we can reduce it. So the last step, because the acetal formation is reversible, so we have step 1, step 2, step 3 will be conditions D. We're going to use an excess of water with acid to unmask the acetal back to the carbonyl. So now we've gotten around this issue of the lithium aluminum hydride. So just like with the aromatic chemistry, when we had to position the substituents on the ring, now it's important that we're able to sequence these things so we conserve these functionalities. So we could say protect, reduce, and then unmask. Any questions? So we have time for one more. So we're starting with 3-pentanone. We see the carbonyl at oxidation state 2. Then in the product, it's 0. And so now what we would use is the conditions with the thiol to make the thioketol. So that would be J. We have methane thiol plus the acid. We've formed the thioketol. And so now in the second step, we need conditions to reduce that. So reducing conditions, so nickel and hydrogen gas, that would be C. So that then brings it down to the alkane. So the next, I think, 3 slides are kind of similar in that vein. Since we're about out of time today, I would encourage you to try to go through them, see if you can figure them out. And then on Wednesday, we'll start with adding these other weak nucleophiles. What functional groups do they form? And so what we're starting to do is expand our toolbox of reactions to access different functional group relationships, and how can we build more complex molecules from that.